Hello again and welcome to this session on unit vectors. In video 4, we left off with saying that the vector A is not exactly equal to the components as expressed as scalars. We needed something. This is a not equals. We needed some way to be able to express A as a magnitude and a direction. We do that using unit vectors. Unit vectors. Unit vectors, when multiplied by a scalar, give it a direction, but they do not change its magnitude. All right, so let's see. Let's set up a coordinate system. Ooh. Yeah. Okay, so we're going to make this up here the z-axis. We're going to make this the x-axis, and we're going to make this the y-axis. Now, by the right-hand rule, just so you know, this has to be, this is coming out this way is positive, and it has to be this way by the right-hand rule, because if you take your fingers and roll x into y, your thumb should point upward into z. Right? So the unit vectors here along x, we have one this way. I'll draw them kind of big just to make it obvious. Then we have one along the y. Oops, that didn't do it. Ah, dang it. There we go. Well, we'll just go with that. Here. Okay, go here. And z. Nope. Try that again. From here to there. Okay. Now, these three unit vectors have special names. In the x direction, it's a lowercase I with a little hat on it. In the y direction, it's a lowercase j with a little hat on it. And in the z direction, it's a lowercase k with a little hat on it, affectionately called I hat, j hat, and k hat. Just so you know, you can also, let's get this 3D coordinate system again. Oh, I don't want to do that in red. So let me get the black, get the coordinate system. Okay, there we go. Okay, so that looks similar to the one up there, but we can also label these as x going this way, positive x, y going straight up the way we normally think of y, and then z, positive z, would be coming out at us. Again, thinking about taking your right hand rule, taking your hands in the x direction, and then rolling them up toward the y direction, your thumb points in the z direction, which is coming out of the page. And you get the same three little vectors. Well, that didn't line quite up, but you know what I mean. Okay, y and z. I should be able. No, okay. All right, and z. let's do that, right? Get rid of that. Erase that. That's the one. There. Okay, here. And let's get rid of that. Here, and go this way. Did it again. There, there, there. Start from the origin. There we go. Well, close enough. Okay, so in the x direction, it's always I hat for the unit vector. In the y direction, it's always j hat for the unit vector. And in the z direction, it's always k hat for the unit vector. Always, always, always. Okay, so the orientation of these axes don't matter. So each unit vector is parallel to an axis. Has a length of 1. So it does not change the value, the magnitude of any vector of length, has a length of 1 and does not have dimensions. Not have dimensions. So it does not change the dimensions of the vector. Okay, so sometimes, so these can be written two ways. Typically, it's I hat, but that's the same as x, j, y, and k is z. And we can write what I just said above in terms of magnitudes. They all equal 1, right? The 3 are all perpendicular to one another. Okay, they only provide direction information. Only provide direction information. All right, so let's generalize how we would write this. So we're going to get our coordinate system here again. Let's get that out here. I'm gonna call this x in this direction, y going up, z coming out at us. I'm gonna give us some vector r. Okay, so r, yeah, that's good. Okay, r, and r now is in 3 dimensions, so r is going to have 3 values of coordinates, x, y, and z. So we can write the vector r as the value of each of these, because each x, y, and z is the magnitude of each of the components of r, times the unit vector. So it would go x times I hat plus y times j hat plus z times k hat. So this is the component along the x direction. So the component of r, little r. Component of r along x. This is the component of r along y. And this is the component of r along z. Right? So, we're going to generalize this again. So, for a vector to be broken down into components of ax, ay, and az, to do that completely, the vector A equals the magnitude in the x direction times the unit vector in the x direction plus the magnitude in the y direction times the unit vector in the y direction plus the magnitude in the z direction times the unit vector in the z direction. Okay, so little example here. Find the sum of two vectors lying in the xy plane. Okay, so A we're given as 2.0i plus 2.0j hat meters, and the vector B is 2.0 I hat minus 4.0 j hat meters. Okay, note that we place the units at the end of the vector. It gets cumbersome if you place them after every component. Just easier to put them at the end. Okay, so we're asked to find the sum. So that means we have to add A plus B. And to do that, we're going to add each component. So A plus B is going to equal the resultant. So to do that, we're going to add, remember, AX, that's going to be AX plus BX in the I direction. And then we're going to say plus AY plus BY in the j hat direction. So let's put the numbers in. AX is 2. BX is 2. And that's in the I hat direction. AY is 2. BY is minus 4. So this is plus or minus 4 in the j hat direction. So this ends up being 4.0i minus 2.0 j hat, again all in meters, bringing our units down. Now you might be asked to convert that they want this in terms of magnitude and direction. So remember, resultant is magnitude of the resultant is going to be not A. It's going to be R, the resultant in the x direction squared, plus the resultant in the y direction squared. So that's going to be square root of 4 squared plus minus 2 squared. Ends up being 4.5 meters. Okay, so let's see, do that. Okay, so we have x, we have y. So in the x direction, it's 4 units. So let me go out 4 units. That's not what I meant to do. Okay, so all right, so we're going to go out 4 units here. 1, 2, 3, 4. And in the y direction, it's minus 2 units. So 1, 2, right there. All right, so right here, this is our R, and here, right here is our theta as officially defined. Okay. Easier to look at it this way, though. All right, so it depends on how you define it. We're going to call this, just to say, I'm going to give it theta prime. Okay, so theta prime, or tangent of theta prime, is the easier one to find. Okay, that's just opposite over adjacent. So that's going to be 2 over 4. Note that I'm leaving out the negative sign because I'm just taking the magnitude here because I'm measuring in the negative direction. All right, so that makes theta prime equal to about 27 degrees. If I look at theta, whoops, let's look at that. Let's try that again. If I look at theta equal tan minus 1 of minus 2 over 4, what I end up with is about 333 degrees, which makes sense. These two should add up to 360. Okay, so just as long as you clearly define what you're talking about, you're all set. Okay, that's it for now. We'll see you later.